Okay, we ended up last time by first defining what a stationary process is. Actually, we said the weekly version of the definition is the one that we are going to use the most. So a weekly stationary process is a process whose first two moments don't change over time. Somebody last time then asked me, but how do I verify if the covariance doesn't change over time? It's not that easy. I mean, it's pretty immediate to recognize if the mean is time invariant. If the variance is time invariant, the autocovariance, so it's called, it's a little bit trickier to verify. But anyway, let's start with the definition and then we see how to apply or verify these concepts. And then we ended up the lessons by saying, okay, this is a very famous process, the random walk. It's very simple, but it's got some use, for example, in finance. And I told you, this is a non-stationary process, and you had to verify if this is actually non-stationary. I told you the mean is actually constant, even though it's kind of meaningless. Now we will see why it's meaningless. But the meaning is constant, and it's just equal to the first observation, which in this case I set equal to 0, as you see from here. But the variance is exploding, so the variance grows together with t's, with the time. But it's immediate to see that if I take the first difference of this process, I get the white noise process. So this is the white noise process. Usually we just use the two letters WN. And what's a white noise process? Is a process whose mean is 0, whose variance is constant, and who is not correlated with its own past, okay? So it's a stationary process because the mean is constant, the variance is constant, but also the covariance, which is always 0, is constant, okay? So this was the first example of a so-called integrated process, because if you remember, we gave a definition of what's an integrated process. An integrated process of order D is a process which is not stationary, but it becomes stationary after D differences, and D is the minimum number of difference, okay? D minus 1 is not enough, okay? So the random walk, which we just saw, is an I1 process. So it's integratable of order 1, and it's because it's non-stationary, we can show that very quickly, and it's stationary after taking one difference, okay? This is important because it's no, we did this consideration last time. We saw that actual time series, they don't look stationary, okay? At least economic one, social ones, they were usually non-stationary. Some have to be stationary. For example, some physical things have to be stationary, otherwise the world would not exist. But some economic and social measurement, they're usually not non-stationary. For example, the GDP of a nation hopefully is not stationary. We all hope that it's growing up, okay? So, but then we said we will be working a lot with stationary process, and then of course the question comes: okay, you tell me we will work with stationary process, but we saw that most of the time series we have to deal with are non-stationary. And what's the binding between the real world and the stationary world? Well, difference is one of these transformation that can make, doesn't have to, but it can make a non-stationary time series a stationary one, okay? So integrated processes, which are processes that are non-stationary, but can be made stationary by taking differences, are an interesting class of processes we're going to work with, okay? And in some way, what we learn from this more theoretical, probabilistic, and statistical part then will be useful also when we'll be reasoning about machine learning, because reasoning about machine learning for forecasting without knowing these things makes you make a lot of mistakes. And I see them when I see just IT people dealing with forecast just with machine learning. Okay. So that's why important to know all these things before also attacking time series with machine learning. Okay, a very simple way to see why a random walk is non-stationary, and it's very useful also for because this operation here is actually this operation. It's the operation of integration. So a random walk is just integrating a white noise. Okay, so if we call, for example, take AT to be any sequence, okay, with T that goes from 1 to whatever, okay. It can be a deterministic sequence, it can be a stochastic sequence, it doesn't matter. If I build a time series doing this operation, then I'm integrating AT. Okay. So if I integrate a white noise, so if AT is a white noise, then I get a random walk. Okay. But in general, we will call this operation integration. And what's an integration is just a partial sum. So it's easy to see. Of course, we need a starting point because this is a recursive equation. So we need some border condition or initial condition. So we can always assume, for example, that y0 is equal to some fixed y. Okay. We could also fix it to a random variable. For a moment, let's just fix it to a fixed number, okay? Well, then by recursive substitution, we can do it. We can rewrite the integration as a partial sum process. So, for example, y1 is equal to this y plus a1, okay? Then y2 is equal to y1 plus a2, but we already computed y1, so we can substitute, and we have, and we have this small y plus a1 plus a2, okay? And then if you go on by substitution, you see that actually, if I take yt, this is just going to be the initial value plus the sum of a, say, j with j that goes from 1 to t, okay? So the part, I can write integration in this way, or I can write integration in this way. So integration is just partial summing, okay? That's why it's called integration. In some way, we use the same terminologies and in continuous mathematics. Integration, this would be an integral, not a sum. But we're in discrete time, so we have a t that is just a counting variable, okay? Otherwise, we tend to use, or difference, of course, differentiation is the opposite as integration. Indeed, we saw that taking the difference of the integrated process will return us, in this case, AT. It's pretty clear that if I take yt minus 1, I get AT, okay? So the difference is the opposite of the integration, exactly as we are using continuous time mathematics, right? Or continuous in R-based mathematics. Okay, so let's go back to our random walk. Well, our random walk is just, we can write this as, okay, there is some initial value. I set this initial value in the former example equal to 0, which is fine, we can do that. It doesn't have to be. But in our case, for example, we had this initial y equal to 0, so we're just summing up white noise, so j that goes from 1 to t of epsilon j. Well, epsilon j is just a white noise, okay, with variance, whatever, okay. So, well, the mean in this case is just 0 because we set y equal to 0. But in general, if I put a different value, if I left the general initial value y, well, the mean is that initial value, okay? However, that initial value is not very interesting because if I suppose that I start observing a time series from period 10 instead of period 1, then the mean changes. So in some way, the mean is not really that constant. I mean, the expectation is constant and it's equal to the first value of the process because the other one are mean 0 process. Now the white noise have mean 0, so if I take the sum, the mean is 0. And so we can say the mean is constant, but it's really not from a conceptual point of view. It's really non-constant because if instead of starting the process from t equal to 0, I start from t equal to 10, then the initial value will be y10, which is non-zero, not equal to this value. Okay, so actually the mean changes according to what's the conditioning first value of the process. So the mean, okay, is constant mathematically, but from a conceptual point of view, it's really not that fixed because it depends on the first value, okay? But it's clear that the variance of yt, well, the variance of yt, we can just ignore the mean because, you know, if I change the mean of a random variable, the variance doesn't change. So let's just ignore the initial value, just take the sum of the white noise. Well, the white noise are not correlated, so the variance is just the sum of all the variances because the covariance is 0, okay? So we're just taking, so the mean is 0, so we can just take the mean of the square of this of this t epsilon j, okay? But they are uncorrelated, so actually I can take out the variant, the summation, because all the white noise are not correlated, so all the cross product will be equal to 0, and so I just get the sum of all the variances. So it's t times sigma square, okay? And it depends on t, so it's non-stationary, okay? So the variance of a random walk is growing together with the time, okay? And so it's not stationary. You can prove, this is another exercise you can do, it's exactly as easy as this one, okay? That the autocovariance of a random walk, so if I take, suppose that we take well, it's easier if we take yt to have mean 0, so but it doesn't change, of course, because I told you the variance and the mean, the variance and the covariance are not subject to the mean value because you take the mean off, okay? So, but anyway, let's just write it more general. So the covariance between yt and ys, so they're just two different times of the same process, is equal to the minimum between t and s and the variance of sigma squared. Try to prove that. Of course, you do the same thing as the variance, but now the timing here will be not the same. One will end at t, and the other one will end at s. Okay, so you will have to keep the one epsilons that get the square and erase all the ones that don't have the same index, because of course the ones that don't have the same index, under the expectation there will be 0 because the covariance is 0. Okay, so you can prove this. Okay, again, it depends on t or s. They're both times. So we see again the process is non-stationary. But it's very easy to see that the difference is stationary because it's a white noise, okay? So we define stationarity, we define order D integration. This is just order 1 integration. But what happens if I integrate an already integrated process? Well, I just increase the order of integration. For example, if I integrate, so suppose this is the random walk, which we know it's an I1 process. If I build a new process, let's say WT, by just integrating YT, all this is going to be an I2 process, okay? And so on, because this is the operation of integration. Okay? Is that clear up now? Okay. And in nature would be real nature or social nature. Usually we find processes, we can approximate real time series with processes usually up to order 2 integration. It's very strange that we could find processes of order more than 2 of integration. Okay. So when we go to the ARIMA process, the I is exactly for integration. Okay. The ARMA part, we will learn about that if you don't already know it. And it's just about the stationary part of the process. So I will be this I here, and ARMA, the ARMA part will be for the stationary part of the process. Okay. Sometimes we already saw that in practice. We applied it to the air passengers time series. We also use the so-called seasonal integration. Okay. So again, we can define a seasonally integrated process as a process we usually use the large D is non-stationary. Let's say is non-stationary. If I take, we already presented the seasonal difference, but then I remember to you what that is, remind to you what that is. So D minus 1 are not enough to make it stationary, but D differences make it, D seasonal differences make it stationary. Okay. Remember that the seasonal difference operator is just applied to a time series, is just taking the difference of YT minus S, where S is the periodicity or the frequency of observation per year. Okay. So in case of a monthly time series, it means I take the difference between an observation and the same and the observation of last year in the same month. Okay. And of course, I can apply it more than once. Here, usually in real applications, we either have 1 or 0 differences. Usually, we don't need more than the 1 seasonal differences. It would be very rare to see 2 seasonal differences. We can have the combination of seasonal and non-seasonal differences. And the nice thing is that we already saw last time, all these operators you probably see for the first time, but you already know how to handle them because they are just like variables as far as their algebra works. So for example, if we apply a seasonal and a non-seasonal operator to the time series, I can expect what the outcome is by just combining these two. Of course, it's commutative, so you can decide either to apply one or the other difference. So of course we can write it at large. Okay, so what we get is just the identity, then we have minus b s, and then plus b and bs. So that would be bs plus 1. Okay, all right. And of course you can verify that by applying first one difference and then the other difference to the time series. And you would notice that you get exactly the same computation. So it's just like the two parts in some way interact, generating one more delay than the large S delay there. Okay. So these are all things we're going to do. So this operation here. So if I, what's the opposite of seasonal difference is seasonal integration. So seasonal integration is just building, let's say, the process yt, which is equal to yt minus s plus at, whatever sequence is at. This is the seasonal integration of at, which is just a sequence. Doesn't matter if it's stochastic. We call this seasonal integration, okay? And the opposite operation is the seasonal difference, okay? So we will call integrated or seasonal integrated a process that has this characteristic. A seasonal integrated process is a process that produces some seasonality, because it means that usually the observation of this month tend to be like the one of last month plus some shock, some stationary shock, if you think it this way. So it's tend to have some similarity with the same observation 1 year ago. Okay, so it generates seasonality in the data. We can simulate from them. So you can also learn how to use R to simulate from this kind of process. I always think it's better to visualize how they look like, because of course then you have to do the opposite operation. You have to look at the time series and then say, okay, I recognize that. I see that it looks like if it were generated by an integrated process or a seasonally integrated process and so on. Okay. Good. No, al momento no. So of course we can, if we want to do this in R, we have two possibilities. One is of course the cum-sum function, so the cum-sum function, so accumulating the sum, because as we see, integration is actually just a partial sum, or we can use the so-called filter function. The filter function, you have to pay some attention because, for example, it's overwritten by the deployers. I don't know if you use dplyrs or deployers, this package for doing, tidyverse data analysis. Probably you're using that. Of course, if you load the deployer package, then the filter function is it's hidden by the deployer ones. You see it when you load the package. It's called, the function is masked by, okay. So if you really want to use the one of stats, which is the statistics package, which is always loaded by R, it's safer if you wanted to use it jointly with deployer, that you always call it with stats filter, okay. So you're telling R, like in Python you always have to do that, okay. You have to, load the library, but then you always have to call a function of a library using the name of the library or the short name of the library. In R, when you use a library or when you call a package, You don't have to do that, but you have to read if the package is masking the function of some other package you have loaded. So, but if you want, like, be sure, like in Python, you can always use this writing. So the two times the semicolon here. Okay. For example, the filter function is very general. It allows you to build two kind of filters. Actually, you always have to pass again a sequence. So we pass a vector with a sequence of, we call it AI, A1, A2, AN. And then you have two alternatives. One is called recursive. It's one of the formal parameters of the filter function, of course. Recursive means that you pass also a parameter vector. Let's call this parameter vector phi. So this is a vector, and well, this is also a vector, which is of course phi 1, phi 2, let's say phi p. You could provide initial value. If you don't provide initial values, it will use 0 as initial values, but you could provide initial values. There's only one funny thing about the initial values. R will use it in reverse order. It's written in the helper for some. But anyway, let's just suppose we don't have initial values at the moment, so we're just initializing the recursive equation by 0. Then it produces a time series. I think it doesn't have a name, so we can call it whatever we want. So maybe YT, and will be just the recursive filter, which is just this way, which we will soon learn to call it an autoregressive process when A are white noise. But anyway, this is just a recursive filter. Okay. So this function produces this thing here, if we call it with the recursive option. And you see, this includes the integration. Integration, we just make phi 1 equal to 0, equal to 1, and all the rest we omit. If we needed the seasonal integration, well, we just pick the largest well, this p will be equal to s. We will set phi s equal to 1, and all the rest will be 0. So we have this special cases. We can get the integration and the seasonal integration as special cases. Otherwise, we can use it with the option. Okay, I'll tell you when it comes to my mind. I'll tell you. But anyway, this other option will produce the so-called moving average in some ways, and it could be a centered moving average or an asymmetric moving average. So there's another parameter which is called sides, which could be 1 or 2. We usually use it with one side because we want models, we want to simulate processes that are based on just on past information. So if it's on just one side, convolution, sorry, it's convolution. Okay. So one side means that it builds, again, let's just call, this is, again, we have to pass, again, a vector of coefficients. In this case, it will be just a moving average, or actually it's a moving, it's usually called moving average. Moving average is not the correct naming because the phi, they don't have to sum to 1. So it's just a moving linear combination of the inputs we're providing. Okay, this is sides equal to 1. Otherwise, if you put sides equal to 2, then it will be a symmetric moving average, meaning that let's assume that P is odd. Then you will have that yt is equal to, if it's odd, well, we have phi 1, which will be attached to at minus, let's say, s minus, or actually p minus 1 divided by 2, up to phi p, which is attached to a p plus p minus 1 divided by 2. Okay, so it's just centering, yeah. Size equal to 2.
Yeah, size 1, the equation. But phi 1, then make a t minus 1, right?
I minus 1, right. Sorry. Right, yeah. It's much simpler if you put this by 0, then you have the same index in here. But in R, usually we start from 1. Anyway, yeah, that's, thank you. And I hope I did this. Is this correct? I'm not sure. Yeah, it's plus 1. It's okay. Suppose let's take 5. I have 2. It's correct. Yeah, I have. Yeah, I have minus 2 and plus 2. Right. That's right. This time I get it. But anyway, the concept is this is symmetric. Okay, if it's even, you have to check the help. I think it puts more. The one extra is put on the past and not in the future. But you have to check the head. Anyway, usually use it with P odd, or we'll be using this mostly of the time. Again, in this case, while the convolution wants initial values, and if you don't provide initial values, we'll use zeros. The convolution, so the recursive one, the convolution instead will just produce a time series yt, which is shorter than the at, because of course it needs some starting values. So before it's able to compute a t, well, t has to start from p plus 1, otherwise you don't have enough past. Okay, so the yt will be shorter than the at. Okay, which is not the case in the recursive. I don't remember if it produces missing observation or just. Probably, no, it doesn't produce missing observation. It just starts from the pth, which will be called t equal to 1. Okay? So, well, this is just to, and this function will come handy in many situations. So that's why I wanted to spend a little bit of time telling you how it works. Of course, you can make it in many other ways. The good thing about this function is that we don't have to produce for loops, because for loops in interpreted languages are evil. Okay, you just have to avoid them as much as you can. And usually, when you have recursive things, you cannot avoid for loops. Okay, but in this case, we can avoid for loops. We have this filter function. Yeah.
So sequence to its integrated.
Yeah, we'll be using this function in many situations. Of course, now I present it because we can simulate some integrated process, I1, I2, season integrated, and I want you to start looking at them because as I told you, when you will be modeling time series, you have to do the opposite work. So you look at the time series, say, okay, that's seasonally integrated. So I wanted to start knowing how they just look like. That's why I presented it here. And we can just do a couple of exercises. In some way, of course, you can make time series analysis automatic, as you can make automatic almost everything now, especially with AI. But actually, okay, if you have to predict thousands of time series, you have no alternative than that. Okay? Just find some good algorithms and just pass the time series. And for example, there are all, I don't know if you ever heard the M1 and M2, M3, and up to M5 competitions. You can find out there. There's this professor of forecasting, now he's pretty old, Makridakis, I think his name, started years ago using this society. It's called the International Institute of Forecasting. They also have a good review. It's called the International Journal of Forecasting. They started this forecasting competitions, I would say 20 years ago. And every so many years, there's a new one. And there they provide you with, at the beginning, hundreds. Now we have like 100,000 time series to predict. Okay. And then there's like a world competition on who's the best forecaster and so on. And in the last, well, at the beginning, it's interesting because in the beginning, linear models were doing better than machine learning models, because machine learning models were not that much developed, and the computational hardness was still too tough for the computers of 20, 25 years ago. But as the competition went on and on, then there was, I think, the M4, which is not the last one. The last one is M5. M4, the best models were like hybrid models between statistical model and machine learning models. And I think in the M5, finally, machine learning took over, and on the average, of course, won the competition. And it was some way deep learning and stuff. But usually, if you have so many time series to predict, you can go that way. It's the only way to go. So in this moment, and usually, of course, at the beginning, there were more like academic teams to win. And the last two competitions, I think one was won by Uber, and the other one was won by Google. So it's moving from, of course, from academics to machine to like big tech society, from statistics to machine learning, because of course they have also capabilities of doing very complex models on that. But the problem is that usually you don't have to predict 1,000 or 100,000 time series. You don't want to win on the average. Usually the business where you work for or just you're consulting for, they want just to predict one time series. So you have to build the best model for that time series, not the best model in the average, okay? And usually, and of course, the nature of the data can be very different. For example, the M5 competition was just retails by, I think, Walmart. But the other ones were more mixed. There were like daily time series, monthly time series. There were time series from finance, from economics, from physics, whatever. So again, usually have to deal either with one time series or maybe more than one time series, but on the same field with the same frequency of observations. And that can make a big difference. So you usually you don't have to win on the average. You have to win on the single time series. And there, your brain is much more handy than an algorithm. Because this is, for example, something I'm not sure I already said that to you, but if you have to get a machine to learn the Easter algorithm, probably you need 400 years of data, okay? But you know that algorithm already. So you know how the world works, and that can help a lot while making a model for prediction, whatever it be linear or machine learning model, doesn't matter. Your knowledge about the world is very worthy when you're building a time series model. So it's, in my opinion, it's good if you start seeing how these processes look like, because then you will kind of recognize these things in reality when you see real time series. And so just to convince you why it's good to become acquainted with all the information we will give you in this course, because pressing a button is good on the average, but it's not. It's really bad if you just have a few time series to predict. Anyway, for example, skip the keyboard. Let's go to R and just simulate a couple of time series. So, for example, let's start with, well, let's just generate a white noise. We can call it Wn. And we, of course, a white noise we can generate from a so-called IID process. You know, do you know what I mean by IID? So independent, identically distributed. Okay. We can take, for example, the classical Gaussian distribution if you want to, and generate some, well, we can fix an n, so the length of the time series. Let's just start with hundreds of observations, 100 observations. Let's simulate from a normal distribution. We can take mean 0, and because the white noise has to be mean 0. Standard deviation 1 is fine. It doesn't really matter at the moment. So we can just look at this as a, of course, anybody of you is generating different numbers, but this is basically what a white noise or a Gaussian white noise looks like, okay? There's zero mean, there is really no persistence, and we will see that we will be able also to estimate the autocorrelation function, which is of course related to the autocovariance function we defined when we defined the stationary process. So the autocovariance is just the variance of xt with xt minus h, for example. This, we know that the autocovariance is 0 here. So let's generate a random walk. Well, to generate a random walk, I can either take the partial sum of this, which is, for example, using the cum sum, or, so let's call it, oops, white noise here, sorry. Okay, it looks much different, okay? Of course, it's smoother. Integration is always a smoothing operation. In continuous time or in discrete time, integration always makes things smoother, okay? If you ever heard about a Brownian motion, well, this is the discrete time version of the Brownian motion. And of course, we can also generate the same process, exactly the same process by using the filter function. We pass the white noise as what x here is called x. The filter is the vector. In this case, it's just a scalar with a 1. And then we have to apply recursive. And the initial value 0 is fine. So this should be just equal to the other random walk we just generated. Okay. They're just two alternative ways to generate the same thing. Okay. As I told you, any of you will have a different version of the random walk because it's stochastic. So, it doesn't look stationary, right? The other one, just by looking at that, it looks stationary. I mean, the mean is constant, the variance looks to be constant. The nice thing here is that actually the mean should be constant and the variance not constant, but the mean is in some way meaningless here, okay? Because if I start from here, the mean is this. And if I start from here, the mean is this one. If I start from there, the mean is that one. So there is really no mean here, okay? And in some way, I'll just give you some information about things we will see later. If you take like the sample mean of the partial sums here, they don't converge. If I take the sample mean of this here, of course, it converges to 0. You can try it. If you take like the mean of the first 10 observations, then 11, then 12, and so on, you will see that this converges to 0 because of the law of a large number, of course, okay? But if you take this process here, the law of a large number doesn't work anymore. Well, it works with a different scaling, so it doesn't, the classical one doesn't work anymore. And if you take the mean of the first 10, then 11, 12 observation, you will see that that mean actually converges to a random variable, okay? It's not, it doesn't converge to a point, as we should have by the law of large numbers, but here it doesn't apply because the variance is exploding. And there is no law of large numbers if the variance is exploding unless you control for that variance, okay? What about if we integrate the integrated process? Let's try just to look to see how it looks like. I don't know, we can call it I2, for example. We can just take the cum sum of any one of the two processes. And of course, what we can expect, it's smoother. It's even more smooth. Okay, much smoother. Well, this process it's called the integrated random walk process because we integrated random walk. So this is called integrated random walk. Sometimes it's also called the smooth trend because it's sometimes used as a model for a trend because I can generate very smooth trends, and usually we like the trends to be smooth. Okay, and this actually could be not the whole time series. It could be just one of the components making up the time series. When we'll go to the so-called unobserved component model, that's exactly what we are going to do. We will use processes to generate just one part, for example, a trend, or the seasonality, or the business cycle. So we will build stochastic objects that are able to reproduce the features we want in these components. And this is of course, a great object to produce smooth trends, which is something we usually like to have. Of course, I can also, this doesn't have to, in this case, we cannot predict if the trend is going up or down. But of course, if I introduce a constant into the random walk, or differently said, if I put a mean which is different than 0, instead of having a white noise, I will have something which is close to a white noise, but it doesn't have a mean 0, has a positive or a negative mean, which is the same as adding a constant. Then I will produce trends like it will be equivalent to like a linear trend plus a random walk. We can simulate that, but it's very simple to. Well, this is called the random walk with drift. So random walk with drift. I don't know, I can put the beta plus, and here we have a white noise, okay? Again, we can make this start from wherever. Let's make it this way. or I don't know, y, let's just call it y. Well, this is equivalent. You can prove that to a straight line plus a random walk. Okay, so this is just a straight line, and this is a random walk. It's called a random walk with drift. It's a mixture of a so-called deterministic trend, because a straight line is just deterministic. We can predict it in the eternal future. And then a random walk, which is a purely, we call it a trend anyway, because it's non-stationary. The mean changes continuously. So the sum of these two is the random walk with drift. Of course, if I take the difference of a random walk with drift, I get a white noise plus some constant. So actually I get a white noise with a mean which is not zero in some way, okay? With a beta mean, okay? So that relates the strength of the trend, how quickly the trend grows to that constant here, okay? Well, these things will be important now that we start with ARIMA models, but will be even more important when we will go to the state space model and unobserved component models, okay? For example, let's just produce a random walk with drift. We can just sum, I don't know, for example, 0.2 plus, sorry, plus. So I'm taking the integration of a Gaussian white noise plus 0.2, which is equivalent to writing a random walk, a normal distribution with 0.2 mean. You can pick whatever you want, okay? This will be, of course, increasing in the average, because of course the random walk could take it also down, but in the average it will be an increasing process, right? And if I change the sign, for example, this will be decreasing, okay? Of course, how strongly you can see it increase or decrease depends between not only the drift, so this is called the drift, but also the variance of the white noise. Of course, the larger the variance of the white noise, the less notable will be the drift. And of course, if you put the variance of the white noise equal to 0, you just get a straight line. Okay. So what's important to see, let's say, the drift part of the random walk with drift is the ratio between, in some way, the variance of the white noise and the drift. Okay. Everything clear? Now let's look how an integrated process looks like, a seasonally integrated process looks like. An important thing in the integrated process, because in the seasonally integrated process, because we are going to use it to model seasonal time series, is the initial values. It's kind of not that interesting to let a seasonally integrated process to have zeros as initial values. We want the initial values to look like the seasonality that time series has, okay, in some way. So, for example, suppose we want to generate, let's say, a quarterly time series. Quarterly means that the seasonality is period 4, okay? It's like quarterly data, like GDP is quarterly usually, okay? Let's just fix some initial values. The seasonality has to sum up to 0 over the year. So we can, I don't know, 10 minus 5, then, I don't know, 0, and -5. So this could be the initial seasonality in some way. So if we want to generate like a seasonally integrated process, or SI, I can use the filter function, of course. I want to apply it also to some to a white noise. I can recycle the white noise above. Then I have, of course, I want a recursive method, but I have to pass the filter. And now the filter will be 0 for the previous value, 0 for 2 lags, 0 for 3 lags, and 1 for 4 lags, because it's quarterly, okay? So it means that I want to produce time series based on, okay? So this is t minus 4, okay? So I have to put to 0 t minus 1, t minus 2, t minus 3, and put equal to 1 t minus 4. Then, of course, I want it to be recursive. And I want to exploit the init to be equal to our init. You will see that actually they will be used in the opposite direction. I don't know why they decided to do that, but this will start from -1, then 0, and then -1, 10 for some reasons. So if we wanted to keep it that direction, we have to reverse it. There are many ways to do that, but it's really not that interesting to keep that. Okay, you see we produced a strong seasonality. The seasonality is evolving over time. Of course, this is not a model for a deterministic seasonality. This is a model for a stochastic seasonality. So a seasonality that can evolve over time. So actually, a seasonally integrated process is a good model for an evolving seasonality, okay? And in some way, if you sum up the random walk with drift and this one, you cannot get time series that look like a real time series. Like, for example, just some, I don't know, so random walk with drift and this seasonality, well, they're kind of different. Well, usually we want to have increase in time series. So let's put it here, increasing. Okay. So, I mean, it looks like it could be a time series, a real time series. Okay? So we're just kind of doing like Lego. We're building like small bricks that we can use to build house, or Lego house, or something like that. As I told you, this will be more what we do when we do unobserved component models. But I think it's good to present them here because also ARIMA models in some way are related to these concepts. And so knowing what we're doing when we take a seasonal difference to make it stationary, or a simple difference, a seasonal difference. For example, this time series, how could I make it stationary? Do you have some clue? Well, let's try it. Of course, if I take a simple difference, I do not eliminate the seasonal variation, okay?
Integrated for equal to a portion, so we can differentiate.
Actually, for this very time series here, the seasonal difference will do the work, will do the job. So let's try to see why. So let's build this this time series. Later, all these things will be clear to you why, but at this point, you just need to believe me. So I'll just take the difference of random walk with drift and seasonal integration. I take a seasonal difference. So this looks stationary. It's not white noise, but it's stationary. Okay. We will learn how a little bit of the algebra of these operations now that we're going to work with the Riemann models. Okay. So actually, the seasonal indifference in some way can take the integration of the non-seasonal parts away. As I told you, now just trust me, it will be clear why this happens in a couple of lessons. Okay. Well, in some way you can understand this by seeing that when you apply, well, in some way this is like applying the two differences. You see, it's not just the sequence of one and the other difference. So again, if I seasonally integrate an integrated process, not the same thing as summing an integrated process with a seasonally integrated process. But anyway, as I told you, things will become clear a little bit later. But of course, we can play it, of course, with these operations. A very important tool that we now present for time series analysis is an estimation of the autocovariance and then autocorrelation function. So if we go back to our stationary processes, we stated that in a stationary process, the autocovariance doesn't depend on time. So the autocovariance in general is a function of 2 points, because it would be like covariance of yt and ys. Okay, this is in general, like for example in a random walk we saw that it's a function of 2 points, because we have to take the minimum, sorry, between t and s. Okay, so for a random walk we just presented this result, which I suggest you try to prove, which is very simple. And it depends on the 2 points. But what we said in a stationary process, it actually depends only, we can start giving the same definition, but if you remember, this depends only on the difference between the times t and s. It's only a function which we could still call gamma of just one parameter, which is the difference between t and s. So it's actually it's not a two variable function, but it's just one variable function. Okay? I just use the same name gamma, but of course they're slightly different. Okay, so usually for a stationary process, we define the autocovariance function either this way or this way, because h is an integer number, and it's of course the covariance between yt, well, minus its mean, and yt minus h minus its mean, which does not depend. So, okay. Sometimes we can, either use the parentheses or not use. Okay. So this is called the autocovariance function of a stationary process. So while in general the autocovariance function is a function of two arguments, because it matters when you compute it. On a stationary process, it doesn't matter when you compute it because it's constant over time. So it just depends on the time difference between t and s, which we call h. And it's very simple to show that it's symmetric. Indeed, I put the absolute value here because, of course, the covariance operator is symmetric in the two parts, and because of stationarities, I can shift left and right in time. Okay. So this is called the autocovariance function. What's the autocorrelation function? Well, it's just the autocovariance function transformed into correlation. So I just have to divide by the product of the two standard deviations, but the two standard deviations in this case are just the same. So by definition, the correlation is just the covariance divided by the square root of the variance of the, in this case, of this part and then of this part. But it's a stationary process, so they're just the same numbers, right? And we call them gamma zero, okay? So the autocorrelation is just the autocovariance divided by the variance. So this is just by the definition of what a correlation is. I take the covariance and I divide it by the square root of the product of the two variances. But the two variances, because it's a stationary process, are constant, and we call it gamma zero. So it's the square root of gamma zero times gamma zero, so it's just that. So if I divide the autocovariance by the variance, I get the autocorrelation. In the autocorrelation, it's just between -1 and 1 because it's a correlation. And it's more interesting usually to look at because it's insensible to the size, to the unit of measurement of the time sequence. So usually we want to estimate this and this, both of them. But usually we look at the plots of the autocorrelation version. Okay? And what's the autocorrelation of a stationary process? Well, it's in some way it's just telling us if the time series has linear memory of its own past. Because correlation is a measurement of linear dependence, and autocorrelation means that we look at how the observation of today is correlated with the previous observation. Of course, if there is autocorrelation, we can use a linear model to predict. If there is no linear correlation like a white noise, in a white noise, our best guess is just the mean, which is 0. Okay? So that's why it's a very important tool. Of course, this is the population. You see, I'm using expectations here. So it's a population or a theoretical value. But in a stationary process, we are able to estimate them by just using the sample covariance. Okay. So we estimate gamma h raw h by the sample counterparts. So, for example, we can estimate the autocovariance function by taking well, we will see the index, how they look like, but here we have yt, well, possibly minus its sample mean, of course, times yt minus h minus its sample mean. So this is just the sample mean, okay? I didn't define it, but This is the sample mean. Okay? This is actually a time mean more than a sample mean, but we can call it both. And of course here, the t have to run from h plus 1 to n, okay? Some of you may say, okay, but why are you dividing by n? Because you're not summing n numbers, you're summing n minus h numbers, okay? It's true. The reason is that if you divide by n minus h, you're dividing by a different number for every h. And since this is a covariance, we know that the covariance has to be positive definite, a positive definite function. What does it mean? That if you put it in a matrix, if you build the gamma matrix by putting all the and so on. So this is like the autocovariance function, autocovariance matrix. You can make it as large as you want, of course, but this is a covariance matrix. So a covariance matrix is symmetric, definite positive, or definite, semi-definite positive, okay? And so must also the estimation, because you cannot, if you want to estimate, so if you want to have here, so you put all the halves here, you want this to behave like a covariant matrix. But if you divide by, instead of n, by n in minus h, this property is not guaranteed, okay? Because you're dividing by different number. And so the positive definiteness property is not guaranteed. So you usually will want to keep that. And anyway, autocovariance is anyway a bias estimator of the population autocovariance. So the fact that we introduce some more bias doesn't really matter much. Also because we are more interested in the shape of this function, not really in the very number, but more in the shape of this function. Okay. So that's the reason why we divide by it. And the software usually divides by it. Okay. And of course, if we want an estimate of the autocorrelation, you just take the I'm sorry. Okay. Of course, there are technical conditions under which the mean is consistent for the population mean, and the autocovariance is consistent for the population autocovariance. Because of course, we are not dealing with IID data. So our YT is now just a stationary process. But we have to exclude some of the stationary process in order for example, for the mean of the process to converge to the population mean. Okay, I don't give you these technical details because anyway, in applications are not that interesting. But in some way, I want just to give you the message. From a probabilistic point of view, in order to be able to apply the law of large number here, I have to, in some way, limit the amount of memory that the stationary process has of its own text. So in some way, the autocovariance, the population autocovariance function has to go to 0 quickly enough. But I don't give you more than this because anyway, in application is not that interesting. If you're interested, I think in my book I put some in this convention. Okay. So we can say what happens to the autocorrelation function, and we can see how it works when applied to simulated and real data. One point, this says in order to estimate and to have sensible estimation of the autocorrelation function, I need a stationary process. What happens if I don't have it? For example, if I compute this on a random walk, well, it's pretty simple. You will see that the memory is very long and the sample autocorrelation function will be very close to 1 for a long time, and then it will decrease, but it will decrease just because we are divided by n. We are just summing n minus h numbers, which will be very close to 1, at least in the correlation 1. But as we are divided by n, by construction, this number has to go to 0, because as h increases, I'm summing just a few numbers, but I'm still divided by a large number. So if I apply the sample autocorrelation function to a random walk, I will just notice something that goes to 0, but very slowly. Another thing, in order to have a good estimate of the autocorrelation function, h must not to be too large, of course, because first of all, because I'm using if I take h almost equal to n, well, I'm just estimating the autocovariance based on 3-4 observations. Okay? If h is very large, then this starts from a number which is very close to n. So I'm just using 3-4 observation maybe to estimate the autocovariance. So h usually doesn't have to be larger than 1/3 of n. Okay? Otherwise, I'm using too little information, and I'm also dividing by n. And divided by n, of course, it doesn't matter if h is small, but it matters if h is large. So never go beyond 1/3 of the time series survey. Okay. So again, let's try to see that on simulated real data using R. So there are two functions in R. One is called ACF, autocorrelation function, which is the one we will be using. Then there is another one we will present later, which is called the partial autocorrelation function, PACF. And let's just, for example, let's just take the autocorrelation function of the white noise. By default, also a plot is produced. If you look at the instructions, okay, of course, we have the time series, which here is called X. Then there is a lag max, which I'm not sure how large is by default. We can learn, but we can fix it, okay? So if I just want to see the first 10 autocorrelations, or I put 10. If I want to see the first 20 autocorrelation, I put 20. Remember that we don't want that number to be larger than 1/3 of the time series. For example, now we have n is equal to 100. I don't know, we can go with 30. Let's just compute the first 30. And you see, you can compute the correlation, the covariance, and also the partial covariance. And by default, it also produces a plot. So let's look at this. For some reasons, the ones that wrote this function decided that it's interesting to see the correlation at lag 0, which is by definition equal to 1. So we'll always start with a 1. For example, if you use the ACF from the package forecast, which is with capital A, you just throw this away, okay? Anyway, this is a white noise. So a white noise, we know that has 0 correlation for positive or negative lags. For lag 0, the correlation it would be yourself. So your correlation with yourself is 1 by definition. Okay? Of course, it's not exactly 0 because this is the sample counterpart. Okay, but if we sample longer time series, so if this n goes to 1,000 or 1,000,000, because of the law of large number, this is going to go to 0, okay? You see that usually software plot also this kind of confidence band for the 0. It means that you could use them to test if a single correlation is equal to 1. But of course, if you look at all of them, you're doing multiple testing. So watch out. In this case, for example, I get all these are 95% confidence interval for the 0, okay? I usually expect, of course, that 5% under the null hypothesis that this is actually the autocorrelation, the sample autocorrelation function taken on a white noise. I would expect that circa 5% of them can get outside of these bands, of course, because I'm testing using the size 95%. It means that I can get an error of 5% of the times in the average. Okay. In this case, I don't get any out of the bands. Probably if you simulate it, you get maybe 1. Anyway, these are bands you can kind of use for, they give you a unit of measurement of how uncertain is your estimation because of the sample that you have, okay? But anyway, you see they're all close to 0 as they should be because it's a white noise, no correlation of. But if I compute the same thing on the random walk, which is a non-stationary process, actually I should not compute that on a non-stationary process because there are no more sensible estimations of the. But as I mentioned before, what I see is I see a lot of memory that goes to 0 but linearly, and it goes to 0 mostly because, as I told you, I'm divided by n, but I'm just summing n minus h quantities. Okay, so the sample autocovariance function of a white noise kind of looks like this. So very a lot of persistence, and it goes to 0 linearly, rather slowly. Okay? And if we do the same thing on a seasonal model, which I think it's called SE, well, it happens something very similar, but it happens on the, leave the 0 out, it's not very interesting. It happens on the multiple of the seasonality frequency, so 4 in this case, so 4, 8, 12, and so on, okay? Keep it in mind, because this is an instrument we will be using a lot for finding a good model for time series, okay? And as you see, it's, again, very slow to go down linearly. It's fine, because this function doesn't even converge to anything. Well, actually converges to ones, yeah. But just because we will be using that, keep in mind how this shape looks like. I think I put you, we will be soon doing, explaining the autoregressive moving average world. And on the e-learning, I gave you many pictures of how the autocovariance function look like for those processes, okay? Okay, now let's go back to our famous air passengers. So, air passengers, first of all, we always have to deal with the problem of the variance that grows up with the trend, and here the logarithm works. One more thing, one more tool that I want to give you. There is actually, the logarithm is a special case of a larger family of transformations we may want to apply on time series. Of course, the logarithm is the most popular, especially if you have like positive values, but it's not the only one. In some ways, all the powers could be good transformations. Have you ever heard about the Box-Cox transforms? Have you ever seen them somewhere? You have. Okay, Box-Cox transform are this larger family of transformation. Actually, a box transform includes all the powers and the logarithm as a special case. I mean, you can find the Box-Cox transformation even on Wikipedia. So. And here, it's not Wikipedia, but it doesn't matter. So this is the transformation. So if lambda is not 0, it's just the power, and then you take -1 and you rescale. So at the end of the day, this is just the power of your y. Why are we taking minus off and then rescaling by lambda? Because if we take the limit of this thing here for lambda that goes to 0, we get the natural logarithm of yt. And so this is like a continuous transformation in lambda. Why is continuity so important? Well, because sometimes we use algorithms that like do numerical optimization, and in numerical optimization, it's simpler to have continuous function because they have, of course, derivatives that can be computed, and we can try to find, for example, the maximum likelihood also with respect to this lambda, for example. But anyway, a tool that I like my students to know, it's not very popular, but I use it sometimes, is trying to build a plot of like the local averages of your time series and the local standard deviation. When I say local, for example, it could be the mean of every year and the standard deviation of every year of your time series, and then you plot it. If there is a relationship between linear relationship between the variance, the mean and the standard deviation of your time series, then the logarithm usually is a good idea. But anyway, any transformation that is able to make the standard deviation kind of independent of the level, so of the mean of the time series, is a transformation that is stabilizing your variance. So let's build this exercise. Of course, inside the package forecast, you have the Box-Cox transform, but you also have like automatic ways to estimate the Box-Cox transform. But I want to show you this thing, which I find to be rather effective. So let's build maybe a new time series for the air passengers by taking let's fix a lambda. Well, lambda equal to 1 means that actually we are applying no transformation. We're just taking -1 and then rescaling. So that would be so air passengers -1 at lambda power divided by lambda. Okay, so this is the Box-Cox transformation, right? So if I start with lambda equal to 1, I'm really not transforming the times. I'm just linearly transforming the time series. Lambda. Okay. Now let's take the vector of yearly means of this time series. For example, we can call it means, or let's call it mu's. I don't know if you know the t-apply function. The t-apply function is very, in the t-apply function, you provide a vector, for example, air passengers. Then you provide another vector that gives the same symbol or the same number to the elements of the first vector that you want to group together. Okay. In our case, for example, we can give the name of the year or the number of the year, and that, of course, will group the time series observations by year. And then there's a third parameter, which is the function we want to apply to the grouped time series. It's like a group by and then apply a function. But it works on vectors, so it's very handy. So for example, air passengers, we want just the, for example, so what's the time of air passengers? The TS object, it's a very simple object. It's a time series object that only has like a slow counter, which is the year, usually a periodic counter, which is the month or the quarter. But then, in order to build the date, it uses just a stupid rule. It takes just the year for example, the first month or the first quarter, and then it adds 1/12 in the case of monthly observation, or 1/4 in case of quarterly observation for the next months or quarters. So January 1949 is just 1949. February 1949 is 1949 plus 1/12, which is 0.8, and so on. So this is how the object TS creates dates. It's a very stupid way to do that, but TS is just a very basic tool for time series. We have better ones, but it's the one that you already have in R when you load it, and many time series which are coded into R are already in this form. So if I take the flow of this time, I get just the year. So this is exactly what I want. So if I take the flow of time, I get just the year. So every observation just. So this is my grouping variable, right? And then I just want to apply the mean. So in this way, I'm just building a vector with the means of the time series, the local means, so every year. And I can do the same thing with the standard deviations. We can do SDS, for example, standard deviation. And instead of mean, I put SD, standard deviation, okay? So I built, I think there is just 12 years of data, so I have 12 means and 12 standard deviations, right? Then I do a scatter plot. When I represent the standard deviations as a function of the mean, standard deviations. Okay. And here it's really clear that we're in a situation where the standard deviation grows linearly in the mean, which is perfect if you want to compute, if you want to transform the logarithm. The logarithm will fix this, okay? But of course you can also, of course, put a regression line if you want, whatever. But anyway, sorry, here I should have chosen not air passengers, but X, okay? Okay. For example, if I put it equal to 0, sorry, here we have just a mistake because I'm dividing by 0. In case of lambda equal to 0, of course I have to choose the logarithm. So I should have put if, okay. But anyway, the point is not how to write the function. So, yeah, Dimi?
Will the power of lambda be only on air passengers and not on air passengers minus 1? When
no, it should be only on the air passengers. Did I get it right or not? Okay, sorry, got it wrong. Here. Right. Okay. But anyway, this was the logarithm. Well, it kind of adjust a little bit. Maybe we can even take a smaller number of lambda. I don't know, maybe minus 0.5. Well, now I even inverted this, but you can play around. This is like a visual way to understand what's the best kind of transformation you can take. Or for example, this is even better. It should be even better than the logarithm. Well, now it's more random. There is really not a relationship between the mean and the standard deviation. But the log is doing good work, you know. I didn't. We should add in 5 minutes. So this is a tool. It's called. I usually call it Box-Cox plot. It's a good way to visually select a number for lambda. Of course, if you look at the package forecast, there are automatic ways to select it. But before stopping, and we go on Friday, I wrote for a work I had to do. It's not finished yet, but it's already working fine. I built a kind of dashboard for analyzing some time series, which I will give you the name on the e-learning. It should be. I think it should be here. Yeah, this is again a shiny dashboard, and it's still a work under construction. So there are some things that are not working. But for example, we can load some data. I can load, for example, even the area lines. I have it somewhere. Here, I have some data. But for example, I have the area line here, but of course, let's take something else like, so this is, for example, the industrial production index for Italy. Of course, I have to recognize the dates, and was able to do it. Here in Explore data, well, this is the time series. And here, I put also the lambda right away for the Box-Cox transform. And of course, you can look the autocorrelation function. And I also put this mean standard deviation plot, so the Box-Cox plot. For example, here you can play around and see, okay, here I see the standard deviation depends kind of linearly on the mean. And you can try to like modify this until you get some line which is almost horizontal. Well, again, the log seems to do a decent job, but I can even take negative powers to get an even better. Well, for example, now it's kind of independent. And the nice thing, you can also look at how it looks like. To me, this looks even too much. I don't know why. It's much too extreme. I would have gone with the logarithm anyway. Well, this is the spectrum. I can present you a little bit about that later. And these are, for example, this is a nice plot. These are called seasonal plots. I'm just plotting the same year on the same plot. I represent the same year using a different line. And you see right away there is a seasonality, and this is COVID, of course. You can just see. This is April 2020, so it's COVID. And that's why it's out of the in some way already asking and some of the questions that we had to ask ourselves when we analyze the time series, and I gave already an automatic answer. Is this time series seasonal? Of course it's seasonal. We see it from here. It's multiplicative. So if I have to choose between not doing the log and doing the log, here's a suggestion: take the log. This is just asking log or not log, not all the other Box-Cox transformation. It's stationary. No, it's non-stationary. Clearly, it's non-stationary for various reasons. Well, one of the reasons is, of course, the non-homogeneity of the variance, but it's got a strong seasonality. We said strong seasonality means that it's not stationary. Okay, and is it trending? Yeah, it's kind of trending. I'm afraid it's going down. This is the Italian industrial production, so it's not good that it goes down, but it's going down. And of course, you can also see what happens if I take a difference. Well, here, if I take the difference, it kind of looks like stationary now, but you see how badly the industrial production was hit by the COVID, but then, of course, got back to the initial values after the lockdown stopped. And this is the bad crisis of 2008, 2009. So the world financial crisis. So you can play around with this, of course, if you want to have something quicker to look at the time series. And of course, you can also take both differences here. In this case, so this is the autocorrelation of a time series that now looks stationary, but even though we cure the stationary, it looks like to be stationary now, but it's got a lot of memory. Okay, is that good? Yeah, it's good because it means we can predict it. If this was zero correlation, would be like predictable just with the mean, which is not a very interesting prediction. Linearly, because this is autocorrelation. So it means I can use a linear model to predict it, yes. I can use a linear model to predict it, yes. Maybe I could do even better than using a linear model. Well, I'll just stop here because you have to run. And we go on Friday.